All right, so for these notes today, we're going to talk about VSPER models and geometry. This is really important because if you take a look at our previous notes, our Lewis diagrams, these show the way that covalent molecules bond and the kind of, the connections that they have and how they're bonded to each other. But this is not a realistic view because in reality, of course, molecules exist in three-dimensional space. And not only do they exist in three-dimensional space, they're also they're not static at all. They constantly are in motion. So a VSPER model or this geometric models are going to help explain more what their three-dimensional shape is. We're still going to talk about them and frequently draw them in two-dimension, but being able to take this out of the two-dimensional and put it in, at least in our brains as three-dimensional, is very cool. So we're going to go over 4 different possible geometries. Now, there are more than these. If we take a look, you can kind of see some of these 4 are written out here. There's examples of them. And we're going to go through a couple of examples, and I'm going to show you some physical models. These are models you can actually make at home, potentially, depending on what materials you have lying around your house. The idea behind this is that once we know what its geometry is and we have a better picture of what it actually looks like, we can figure out how those molecules are going to behave around other molecules. For example, the last couple topics we have are whether or not a molecule is polar or nonpolar. The geometry helps determine that. We can't figure that out without that. Once we know if something is polar or nonpolar and a few other features, we can figure out intermolecular forces, which explain help to explain a lot of different features of molecules and substances. For example, why does rubbing alcohol evaporate on your skin but water doesn't? Why does dry ice sublimate at room temperature? A lot of these kinds of ideas, and like is normally a gas at room temperature. So we're going to be able to answer a lot of questions like that. So that's sort of where we're headed, the underpinnings of all of that. So let's dive right in. So here's what you need to know about VSPER models. VSPER stands for valence shell electron pair repulsion. That's what VSPER stands for. And here's basically what it means. Electrons repel each other. That's literally the whole thing. Anytime there's an electron, whether that electron is in a bond or if it is a lone pair of electrons that are just kind of freely moving about, they are going to repel each other. They're both negatively charged. That makes perfect sense. So once we have, we start building bonds and molecules, we can kind of see how those pairs of electrons interact and how they repel each other, and that affects the shape of the molecule. So let's try building one of these. I'm going to use these little styrofoam balls, and I have a couple sizes of styrofoam balls, and I've got just some pieces of pipe cleaner. Oops, sorry. I gotta move this a little bit. It's a little out of my reach. One moment. Yeah, I like that. That's a lot better. So here, the pink is good. That way you can kind of see it. Okay, so we have these shapes here. I also have this, which is just a pair of electrons. That's what that represents. So we can kind of have a good visual of what these electrons are. So as we start putting together these molecules, we'll kind of have a visual for it. So let's take a look at one of the examples from before. Wrong spot. Flip this over. Okay, I think CH4 is a great place to start. So CH4 is a carbon molecule or atom in the center and has 4 hydrogens, one on each side. So what we need to do is put together a model where all of the electrons are as far away from each other as possible. They're so far apart that they can't move any further apart. So let's see if we can make that happen. So this was the drawing that I had done before. Perfectly reasonable drawing, makes perfect sense. But let's see how it actually holds up. Sorry. Making some small adjustments. Okay, perfect. There's our model. So CH4. Okay, well, taking a look at this, according to our VSPER model, there's two rules. Electrons and bonds repel each other. Lone pairs of electrons repel slightly more. All right. Well, we don't have any lone pairs of electrons here. We just have electrons and bonds. So a bond is basically a situation where the electrons are sort of more concentrated in a particular area. This model is still not perfect because it's not really like bonds don't exist as like sticks, but at least it kind of gets us some of the point here. So the bonds, the electrons tend to be fairly concentrated in these bonds. That's where they tend to spend most of their time. So right now, are all of these electrons as far away as possible? Well, if we look at it in just one plane, it looks like it. But as soon as we turn it around, we realize they're really, these electrons are really far apart from each other, like 180 degrees. So they're going to kind of move a little bit. So what if we kind of start moving these around? And this is kind of like what would happen in real life. Okay, so this kind of helps. I don't know, it doesn't really help very much. You can kind of just try moving these. Now, you at home, if you have, you might not have a setup quite like this, but you could try this with maybe like gumdrops and toothpicks, or pieces of pipe cleaner and Play-Doh, or grapes and toothpicks. There's lots of cool things you can try. But anyway, as we start kind of moving these around, like, oh, look, these two seem really close together. So maybe, and here, so maybe if we move it back this way, that's a little bit better. No. You just kind of have to keep finagling with it until it seems like they're all just about as far apart as you can. And you'll start noticing, once you think in the third dimension, it gets a little bit easier. And I think eventually you'll end up with a shape that's kind of like, about like this, where each, bend it just a little bit, that should work, just to kind of get the right, where each one of these is just about as far away as they can be. And if they tried to move them, they'd get too close to one or the other. Okay, so this is a three-dimensional shape that in fact is the general shape for carbon tetrahydride or methane. Now, obviously in real life, everything is wiggling around. There's lots of movement. You know, that's why I like these bendy pipe cleaners for this. You know, they might kind of come close together, but then immediately bump apart again or get close or try to move in different directions. Technically, these bonds are stretching outwards, but they get tugged back in. They're rotating. They're just lots of wiggling. But on average, this is where they like to spend their time. So we would call this shape is called a tetrahedral. So if we take a look, we have four options. Actually, let me come back to that in just a second. We can go back to the names. We can deal with that later. But this is one of the shapes that is possible for that to form. Okay. We'll come back to that in just a minute, but there we go. So let's take a look at this next one. This next one is not the same as carbon tetrahydride or methane. It's one nitrogen with 3 fluorines. So let's make it like we kind of put this back together. So this is one nitrogen and it has 3 fluorines. I'm not going to do all the lone pairs of electrons for fluorine because they're not involved in bonding, but it does have a lone pair right here. Okay. So that's sort of like what we drew before. So the 1, 2, 3 fluorines, 1, 2, 3 fluorines. There's a nitrogen in the middle and there's the electron. Let's flip it around so we can see it better because of the yellow. Okay, again, this is not going to work. We've got electrons in this bond, electrons in this bond, electrons in this bond, and then this lone pair of electrons. So we need to, again, wiggle everything around until everything is as far apart as it can be. 1 second. Gotta get the lights back on. And sorry, while I was up, I started moving it. You can kind of see. If we move everything around a whole bunch, I think we find a shape that's kind of like this, where wherever we turn it, all the electrons are pretty much as far away as they possibly can be. So that's again the VSPER or valence shell pair electron repulsion. So the valence electrons in their shells repel each other. Okay, and so this shape is kind of similar. Now, there's one thing to consider, that electrons aren't like an atom. They don't really have a lot of mass, and they actually freely move wherever they want to go. So this electron pair is here, and it's definitely acting to repulse these other bonds. But in reality, we wouldn't really think of this as part of the molecule and part of its geometry, because they don't really have a lot of mass and they're not really in a distinct spot. So we can even actually, after we've figured out how it affects this particular shape, we can actually just kind of take it off. And there's our new shape. So you can compare it to the shape that we had before, which looked, I got a separate one over here, a little bit more like this. This one's kind of different. They're similar, but not exactly the same. Okay, so let's do one more. Let's do the silicon dioxide. So, and then maybe we'll do water as well, because water is a great one. So silicon dioxide is, hold on. Let's do water first, and then we'll do silicon dioxide. Okay, so water is H2O. I don't even, oh, it's over here. Oh, see, I already did it. I couldn't help myself. Okay, so water is one oxygen in the middle, two hydrogens on either side, and it has two lone pairs of electrons. Okay. But you'll notice I didn't draw it that way, and that's because I know about this whole modeling, this whole diagram thing, that this is not correct. In terms of geometry, this doesn't actually make any sense. Instead, it's got to, again, we got to move everything, wiggle everything around until they're all about as far apart from each other as possible. And if we do that, we end up with a shape more like this. So there's the two electrons. That's why I always draw it this way. It's just a habit, force a habit. If we take these electrons off, now that we've seen how they affect, so we've got these two electrons are repelling each other, the electrons in each of these bonds are all repelling each other, pop those off, and now we have this shape, which is more like how I drew it. There you go. I know, shocking. Okay, let's check out another one of these. Let's do the silicon dioxide. So silicon dioxide has, I kind of already made a model for it, but here we go. Silicon dioxide has a silicon in the middle and an oxygen on either side. The oxygen has electrons, but like we're not too worried, but we actually could pop them on if we wanted. It's got two pairs of electrons. We could throw them on. I don't think it really changes much, but again, we're not really concerned about lone pairs when it comes to geometry. But in this situation, the silicon doesn't have any lone pairs. So the farthest away electrons can get in any direction is 180 degrees. And that's pretty much all there is to it. And once we pop these electrons back off, they don't really have much of an effect. They're just kind of off on the ends. Okay, so that's another shape that we can come up with. All right, so what we end up with are 4 shapes. That's what we'll go over right now. So your job a lot for most of these is when you see a molecule to say, do you think it's linear, bent, trigonal, pyramidal, or tetrahedral? So let me show you an example of each. The first one that we looked at was this one. And based on these names, I think you could probably guess that this one's going to be called tetrahedral. We're going to call it tetrahedral because it kind of has 4 things coming off of it in a shape. Like that's kind of what tetrahedra means. And this is actually the shape, this is actually a shape called the tetrahedra, tetrahedron. So an example of that is CH4. And we can actually draw this more 3-dimensionally to show that shape. If you want. So that would be a way of showing that a little bit more. What this basically means is that there's a hydrogen sticking straight up. There's a hydrogen off to the side. One of the hydrogens is projecting forward and one is projecting back. And that's what those lines mean. The little dot, dot, dots are backwards. The little filled in triangle is a projection forward. So it's a way of showing that a bit. So this is a tetrahedron. So sometimes you will find tetrahedrons around. Okay, the next one we talked about was this one. Okay, and this one has its own, a different shape. It's got this lone pair of electrons. So once again, let's pop that off because that's not really part of the geometry, but it does help inform what shape it is. And if you had to guess of the three, I think trigonal pyramidal makes the most sense because it's pretty much a triangle pyramid, like there's some space under here. So a good example of that was NF3. Okay. And so to draw that one out, maybe we would do something like this. Something like that. Again, to show that three-dimensionality. But labeling this trigonal pyramidal is pretty good too. Okay, the next one I did was water. And you guys saw that. Let me grab it here. Oh, I'm gonna put those lone pair of electrons on back on. That might be kind of helpful. Okay, here's water, the H2O. And you can probably imagine if we pop those off, this is definitely bent. Ba-doop, ba-doop, pretty obvious. And again, a good way of drawing that is just showing that it is bent instead of drawing it as a line. Because water is not linear. It's very much not linear. The world would not exist if water were linear. And by the world, I mean like human beings. Okay, and then finally we had linear is a line. So silicon dioxide is a great example of that. And we can just draw exactly as we would draw it. Okay, so that's one thing you need to know. The other thing is that can come up sometimes is the bond angle. Now the bond angle is, it's the angle between these bonds. Let me see if I can see where it's written. It's like, it's a really bizarre, it's a very bizarre number. It kind of comes up in the lab, but what you'll kind of see is that for a linear molecule, we're looking at this angle right here. You can also think of it as this angle, any direction. What's the angle of that bond? In this case, it's 180 degrees. It's pretty straightforward. Okay. For the other molecules, it is, hold on just one second. I got to pause this just for a moment. So if you, for bond angle, it's the kind of thing that comes up. The bond angle here, again, each of these angles should be the same. This is the tetrahedra. If you do the math, which I frankly don't know how to do, but I know that you can do it, you will find that the bond angle for tetrahedra are 109.5 degrees. I don't know if you need to know that. It doesn't really come up often, but once in a while it's useful to know. More of an AP kind of thing, but there we are. For the trigonal pyramidal, the bond angle you would think would be also 109.5 degrees because it's really basically the same shape. The only thing is this lone pair of electrons actually has, according to number 2, they have repel slightly more. They push down just a little bit extra. So the actual bond angle ends up being 107 degrees instead. And the bent, again, these two electrons push even more and make it more like 105. So if that ever comes up, if you see that, those are some of the bond angles that are associated with these different shapes. Okay, so I think it's time to move on and do some more examples. So let's grab your packet. You have 2 pages in the packet that goes with this, so it's not a lot. So we've got the rest of page 11, which we already started, but we have to do this VSPER now. And then you also have page 12. Oh gosh, you can't even see the 12 there, it got cut off. 12 is all about the name and sketch the shapes of each molecule. So that's pretty cool. There is also this POGL that you might find helpful. It involves drawing out some shapes and, oh gosh, let's see if I can turn the page. Maybe if I put this marker down. There's some more models there. You know, if you think that's interesting and helpful, you should definitely check it out. Okay, so let's actually do a couple of these problems. So here's what we actually need to do. If you look at this, it just says label them with their geometry. So we have 4 choices. So of some of the ones we did here, silicon, let's check out this one from last time. So silicon tetrachloride, do we think it's linear, bent, trigonal, pyramidal, or tetrahedral? Looking at that, it's definitely tetrahedral. That's all we need, just labeling. How about this one, HCN? I actually made a model for this one because it's kind of fun. This is the hydrogen, that's the carbon. It's triple bonded to the nitrogen. This is linear. Okay. How about PCl3? Well, I'm thinking that one looks like 3 things bonded, but it's got this lone pair of electrons. That's got to be trigonal pyramidal. Okay, and let's just do one more. I want to do this OBR2 business. So let's do the Lewis model for it first. So there's oxygen. Oxygen has 6 valence electrons. Bromine has 7. What, there's 2 bromines? Yeah. So it looks like they're going to connect here and here with here and here. Let's put oxygen in the middle. Okay, so if we do that, that looks like it's pretty much linear, right? No, it's not linear. You have to remember that these lone pairs of electrons have an effect. So I almost think of it like a tetrahedron, but if you just remove those electrons, the shape is actually going to be bent, just like water. So it'll be just like, gotta find that model, just like this one, right? So there's the oxygen, there's a bromine, there's the 2 pairs of electrons. So lone pairs of electrons, there's a reason you have to put them in your Lewis models. It's so that you know what the geometry is. Otherwise, it will be very confusing. Okay, so what you can do is go ahead, you've already drawn the Lewis models for all of these at this point, hopefully. So you can go ahead and figure out the shape based on that. For this one, actually, sorry, skip the shape on this one. It's like there's a lot of shapes going on. It's not, there's too much there. It's not linear also. It's like a weird zigzag kind of thing, so don't worry about that. You also can do this page and you can draw the Lewis models first. So let me just pick out like a random one to give it a go. What would be fun? I already did HCN on that side. It's a bad one. We should have picked something else. We've already done water. Let's do number 11. That one looks kind of fun. Okay, so we've got carbon has 4 valence electrons, hydrogen has 1, chlorine each have 7, and there's 3 of them. So it looks like carbon should be in the middle. And then we're going to have a chlorine attached, another chlorine attached, 3rd chlorine. It doesn't really matter which order you put these in, but then this one's going to be a hydrogen instead. So the shape of this one should be, well, it's a central atom with 4 things attached. That sounds like a tetrahedral to me. And we could, if we wanted, we could redraw this to make it a little bit more obvious. Maybe not necessary, but kind of fun. Definitely a tetrahedral. So that's its 4-dimensional shape. 3-dimensional. Anyway. Okay, so that is that. I want to hop in. No, that's not it. Where do I want to hop in? Just to my YouTube site. I did find this is a great video. I'll probably show it in class, but this one's really great. This what is the shape of a molecule? And again, the key point here that I wanted to make was
But for every molecule, there's at least one way to arrange the nuclei.
that we're taking, the whole point is to take flat two-dimensional models and bring them into the third dimension. So
And electrons,
check that out.
so as to maximize the attraction of opposite
Three-dimensional.
and minimize the repulsion of.
And you can do it for very complicated big molecules or very small ones like we did. Okay, so get to work on that one and we'll move on to more properties of molecules for the next one. Thanks.